Hi everyone, here we are at this session for the Blazing Fact Directory Tree Traversal, Haskell Streamly Beats, Rust by Harendra Kumar. Welcome Harendra, thanks for having this session with us. And we are glad that Harendra can join us. Harendra, over to you.
All right, thank you, Samiksha. Let me share my slides now. So let's start with the overview of the talk. So this talk is about directory tree traversal in a functional style. Usually, tree traversals are fundamental to computer science and other languages like C and low-level languages. They have mastered the art of tree traversals, and they are very good at performance as well. Usually, when I go to any Haskell talk and people talk about how do you do graph traversals in pure functional style. So today we'll talk about how we can do that elegantly in a functional manner, in a modular manner, in a composable manner, and still have the performance that matches or surpasses C or Rust. In this talk, we'll talk about a simple program for a directory traversal in Haskell, then improve it incrementally, bit by bit, and get to the performance that is close to the level of C or even better than that. We will talk about first simple plain Haskell directory traversal, then write it in Streamly in a streaming manner. Then we'll talk about some pre-traversal combinators in Streamly and BFS and DFS traversals. Then make it concurrent and see the concurrent pre-traversal performance, compare it with other tools that are available. And then we'll talk about how why Haskell is faster than Rust, what could be the reasons that Haskell cannot perform Rust, and then some performance lessons and takeaways. So let's dive into it right away. And this is what you are seeing. It's a simple Haskell program to do directory traversal. This is a very naive program. This is, in fact, you can ask ChatGPT to write it and it will give you a similar program. So here, I hope my pointer is visible in the video, Samiksha.
Yes, it's visible. Yeah.
Yeah, so here we have a list directory call, which gives us the contents of the directory, which basically underlying system call is get dns on Linux. We are talking about Linux here in the most of the talk. This program will run on Linux. Then we get all the contents of a directory. Then for each path in the directory, we see whether it is a directory again. If it is a directory and it is not a symbolic link, then we again list that directory and do this recursively. So we can see here, we do list dir again recursively if it is not a symbolic link and it is a directory. Otherwise, we just print the particular path. So this works pretty well functionally. We'll test it out on, so this slide gives you the setup for testing. There are 10,000 total directories, 50,000 files, so total 60,000 nodes in this file system tree. Maximum depth is 20 levels, breadth is 500 files. We are not doing a very big directory test, but that would have been useful. We just missed it. Symbolic links are not followed. Now, what are the parameters against which we are benchmarking? We'll measure the wall clock time, the CPU time, the memory, amount of memory that it takes, the peak resident set size, and the number of Haskell allocations for performance improvements. Now, what are the benchmarking tools that we are using? We're using the bash built-in time command for measuring the CPU time. For measuring OS memory, we'll use the time minus v standalone command, not the built-in one. And for Haskell allocations, we'll use plus RTS minus SRTS options. Now let's do the whether the program, check whether the program is giving us correct output. We did a GNU find on that dataset directory, and it gives us 57257 files and directories. This is the number of words, this is the number of characters in the output. And it exactly matches with this program. So the output is exactly the same as find. Now let's see the performance. The timing of find, we are redirecting the output to dev null so that it doesn't, the printing of the output doesn't affect the performance. Now the real time is 184 millisecond. If you see user plus system, that is also equal to 184 millisecond because we are measuring it with hot caches. We ran this command already so that everything is in the cache, and we are doing the CPU bound performance test here. Now, our naive program is taking 454 millisecond, whereas find is taking, the GNU find is taking 184 millisecond. So this is not bad for a very simple Haskell program, the first go. Now, if we measure the allocations that are happening, there are 458 MB allocations, almost half a GB allocations happening in this program while we are running this over this data set. Now we see wall clock time is equal to CPU time, which means this is the CPU bound test. Both are equal. Now, what is wrong performance-wise with this program? Functionally, this is correct. This is perfect. It gives the same output as find. But performance-wise, the list directory buffers the entire directory. So it's not streaming. It won't work on big directories. That's a problem. Now, it also uses string for paths, the string representation, list of character. And Haskell lists are not that well performing if you use them at heavy scale. That's another problem. We do an additional stat system call to check whether it is a directory, and one more stat system calls to check whether it is a symlink. And then for each, printing each path, we are doing put strln. So we are doing as many put strln as there are files in this directory tree. So you can see this here. This is for listing the directories. We are doing one more stat here, and then we are doing a system call to print each path, which is very bad for performance. Now let's improve it a little bit. So we'll remove this one using the list directory using the Haskell strings. So this problem we'll remove in the next version. We'll use OS path instead of strings. We just replaced the string with OS path here. And we do the same, exactly the same thing with this as we did with the earlier version. Now with this, we got 382 millisecond versus 454 earlier. And the allocations reduced a little bit, 441 MB, 16% reduction in time and 4% reduction in allocations with just using the OS path. Now we are at 382 millisecond. Now let's improve it further. Let's remove the next problem. We were doing 2 stat calls in the earlier version. We'll write a little lower level program here to remove the 2 stat calls and do it in a more efficient manner. So we are using the C call here directly to read. We are using the C read dir call. And then the read dir returns the type of the node along with the directory entry. So we'll get the type for free. Whether it is a directory or not, whether it is a symbolic link or not, we'll get that for free. So we basically remove the 2 stat system calls here. And then we are again doing exactly the same thing. We are doing a loop dir here, recursing. Again, if it is a directory, we are doing a depth first search here. Now let's test this out. We get 250 millisecond here compared to the 382 millisecond in naive OS path version. Now here, you see the allocations are 386 MB, so 13% reduction in allocations and 35% reduction in time. Now, what are the issues with this program? We are still doing one put strln call for each path that we are printing, which is very bad. One system call for each, or at least a library call for each path that we are printing. Also, we are converting path to string for printing. Code is low level. It doesn't look that great, that elegant as it should be in Haskell at a high level. And it is still slower than find. Though the code is much better than C, it is still not as elegant as we would want. Can we do elegant and performant at the same time? Let's see. Now, this program that we wrote, the low level, we'll build a modular building block from this, which is available in the Streamly library as read either paths. It takes a path and it returns either stream. Left is the directory in that, and the right is a file. The lefts are directories, rights are files. So we can basically read a directory into a stream, which gives you files and directories separately, distinguished. And it uses the same low-level program that we wrote just before this. But we wrapped this into a nice streaming combinator. But how to perform the recursion that was present in the previous code. So we have a combinator called concat iterate in Streamly, and several versions of that. What it does is it's like concat map, but it iterates over the output stream. The output stream, whatever it, so this function a to stream AMA will generate a stream from each element in the input stream. And then from in the generated stream, it will keep iterating this in the same way. Again, for each element, it will do, it will map this function again, and it will keep on doing this forever. This is just similar to the standard iterate function in functional programming, except that it is a streaming version. It is lifted to streaming. We'll use this function to traverse a directory tree. This is something unique. This is something new in Streamly. I haven't seen such a combinator in any other library or in functional programming before. So let's apply concat iterate to our directory traversal problem. For illustration, we'll use a more concrete type here, where we are taking, so it's the function is taking either dir file, and it's generating a stream of either dir file again. So directories are left and files are right in the either type. And this is the single directory traversal function here, which we will iterate over the stream. The stream that it will generate, it will run again on the same function. So that's the job that concat iterate does. This function here generates either child stream on the left nodes, the left types of either, the left constructor of either is directory, so it will generate a child stream. And the right constructor, it will generate a nil stream because files can't be traversed. Now the stream output is fed back to iterate, and it keeps on iterating over the entire stream. Now let's do depth first style iteration. So there is a concat map with combinator in Streamly, which can take a function which combines the output streams generated by the mapped function in different ways. For example, you can append them, or you can merge them, you can interleave them. In the same manner, we have concat iterate with, which will take a combining function, the stream, which this combining function combines two streams and generates a stream. Now, this combining function is used to combine the streams generated by this function mapped over the input stream. This function is going to generate streams from each element of the input stream, and those streams are combined in this manner using this function. Now, concat iterate functions that we talked about is basically concat iterate with streamk.append. Streamk is the CPS version of a stream, a continuation version, continuation passing style version of stream. Now, the append function of that we pass as the combining function here in concat iterate with. So we are basically appending all the streams together, generating a concated or flattened stream. Now, for breadth first style, we use a different combinator called merge iterate with, which basically takes the generated streams pairwise and then merges them. And then the merged streams, it takes pairwise again and merges them again, so thus creating a kind of a balanced tree of the merges, and finally merges into the top, at the top level, merges the two streams. So this basically gives us a breadth first style kind of traversal. So here, merge iterate with streamk.interleave we will use. So this function is interleaving, which basically merges two streams together in an interleaved manner rather than appending them. It will take one element from one stream, then another element from the other stream. Now, how do we do parallel traversal? We just use a par concat iterate, which is a parallelized version of the concat iterate combinator, where it can do iteration over multiple elements of the stream in parallel. Now, parallel also has different variants depending on the parallelization configuration, where you can give a ordered configuration or interleaving of the streams or first come, first serve kind of style. These are standard combinators in Streamly for merging parallel streams. You can also specify max threads or max buffer, etc. All concurrency parameters you can specify in that. Now for graph traversals, so graphs are basically trees with cycles where you can have cycles. For graphs, you want to know whether a particular node has already been traversed or not. And if it is already traversed, because it can have cycles, so you don't want to keep going in cycles. So you can use a state using the concat iterate scan combinator. You can thread around a state in this, and you can remember things in the state. And it will do exactly the same thing as concat iterate, except with a state. Now, let's create a directory iteration function using our read either paths function. So read either paths function that we talked about earlier. Here, it takes a path, it generates a stream of directories and files. Now we will adapt it to work with our concat iterate function because it needs to take a either type here, and it needs to generate a either type. So on the right type, it will not do anything. On the left type, when we have the left constructor, it will generate a stream from that, generating a stream of the directory contents. Now here, we are writing a program in a functional manner to traverse a directory tree. So here we start from the initial directory, which is dot, the current directory. Now on dot, it will generate a stream from the contents of dot, and then it will continue iterating on that stream until all the directories in that are iterated in the depth first style manner, because we are using the append function for appending the streams. Now, the output of this stream will be all the directories and files that are generated by concat iterate. Now, these directories and files, they are arrays here. The path type in Streamly, its underlying type is an array. Now, these we are converting these paths to arrays, and then we are using unfold each end by combinator to append a new line to each path. So we are unfolding each path using array.reader. We are reading the arrays and appending a line, ending it by a new line, and then combining them into a buffer with 32K size. So all the paths are now batched into a 32K size buffer, and then we are giving it to the standard output handle. Now let's see how this particular program performs. What we did in this case is we are batching the paths. So we are not doing individual system calls, individual put strln for each path. Instead, we are doing one IO for the entire buffer of 32K. Now with this, we get 184 millisecond time, and the locations are 161 MB. So now 26% reduction in time over the data stream version that we had, and 58% reduction in allocations. And the performance is same as GNU find, which was 184 millisecond. GNU find was the same. And code is perfectly modular, but we are not done yet. So let's improve it further using a chunked stream. We were doing one single path to one single path stream at a time. Now we can take a combinator which takes multiple paths, multiple directory paths at a time, and then generates a bunch of files and a bunch of directories in chunks. Now this combinator is called read either chunks in Streamly. Now we will use this combinator in that same program here. Instead of using read either paths, we'll use the chunked combinator instead. Now we got 144 millisecond here, and the allocations are down to 32 MB. From the initial 450 MB or around 500 MB, we have come down to 32 MB allocations here. From the previous program, the batched Streamly 1, we got 22% reduction in time, in CPU time, and 80% reduction in allocations using this batching. And we are better than GNU find now, which was 184 millisecond. We are at 144 millisecond. Code is still perfectly modular, and we can still improve it. Now, byte array output. So we'll, instead of generating paths, a list of paths, we'll be generating a byte array output directly from our directory reading combinator. It takes a list of paths, directory paths, and then generates the output paths in an array. So it directly batches it in the combinator itself, rather than threading them around in the entire loop. Now with that, we are down to 134 millisecond, 20 MB allocations. So we got nice reduction in allocations, 7% improvement over the chunked Streamly version before. This is the fastest serial version of the program yet. It can be made better. Still, there are some improvements in the pipeline, but probably not a lot. 15, 20 millisecond more we can shave off from this. Now let's come to concurrent traversal. This, up to now, we were doing serial traversal only. So in the pipeline, we'll just replace concat iterate with par concat iterate. And now we got 171% CPU utilization. So our time got reduced to 85 millisecond. The CPU time, as you will see, is 146 millisecond, but the real time is 85 millisecond because we are using 2 CPUs now. So that is the best that we could get from this. Now, as an exercise, you can write it in your favorite language and check the performance. And you can use GPT as well to write it in your language. Now, let's do a comparative performance of multiple different tools. We'll use the GNU find, and there's a BFS tool written in C. GNU find is written in C. The Rust FD tool, which is also considered quite fast, written in Rust. Now, list there is the Haskell program. FD does only DFS. The BFS does BFS and DFS both. Find does mixed and DFS. List-dir can do BFS and DFS, but we'll use the best mode of each one of them. They are kind of similar on this data set. So first we ensure that all of them are doing the same work. They are giving us the same number of files and the same number of characters. Here there's a difference of one file. Probably these are not printing the dot or dot dot one of the directories. Now in comparative performance, we'll take these cases, IO bound cases and CPU bound cases. In IO bound cases, we'll do with cold cache. We'll clear the cache on Linux. We'll use this command to clear all the caches. So all the caches are dropped and the caches are completely cold. So everything will be brought from disk using IO. In the CPU bound cases, which we already did before, we'll use hot caches, running the commands once or twice before measuring them. And then we'll do serial and concurrent performance. Now here is the comparison table. BFS is the fastest in this case, which is the C program. In real time, it takes 112 milliseconds. List-dir takes 134. GNU-Find takes 187, and the Rust FD takes 175. But you can see it is using 173% CPU. Others are using only 100%. So this is not serial. This is still doing some concurrency there. So there's something wrong with the program. Though we are passing FD minus J1, which is supposed to be using a single CPU. Now, concurrent performance. So this was the serial performance. Now we will be using concurrent performance with hot caches, CPU bound performance. List-dir is taking 84 milliseconds, as we saw earlier. BFS is taking 125 milliseconds, and FD is taking 140 milliseconds. So here, list-dir, the Haskell is clearly the best. And even CPU time, if you compare, 149 milliseconds versus 200 and 262 in Rust. So list-dir is significantly better than the BFS or FD, the C or Rust versions. And even if you see the peak memory that it is using, it's using 22.5 MB. And these are using 56 MB and 40 MB instead. Now let's do IO bound comparison with cold caches. We use the drop caches configuration to drop all the caches, page cache, inode cache, everything will be cleared up, and then we'll be measuring. Now the timing is, find is taking 6.9 seconds. List-dir is again taking 6.9 seconds. BFS is taking 7.6 seconds, and FD is 7 seconds. So CPU time, we can see the best timing CPU time is BFS, even though its total time is more. Then find is 917 milliseconds, list-dir is 1000. Rust is the worst, 1.6 second here. So not sure why it is not performing as well as others. But FD minus J1 is likely not single threaded. So there's something wrong with its FD minus J1 option. Now let's see the concurrent versions in IO bound cases. List-dir is taking 5.9 seconds. FD is similar time. BFS is taking more time. Now, if you see CPU time, list-dir is taking much less than FD. The CPU utilization is 15%. It's FD CPU utilization is 23%. If you look at memory, list-dir is taking 19 MB and FD is taking 40 MB. As an exercise, we can write the FD-like program in Streamly. If anyone is up for it, please do it. With all compatible options, we can do DFS, BFS, but we'll need regex library as well, because these programs, FD and BFS, do quite a lot in terms of filtering the files as well. Now, performance lessons. Allocations in Haskell are not very expensive. The reduction in allocations was 25x, though CPU time got reduced by 2.5x around in the first version and the final version. But they definitely indicate other perf issues in the program. So it's good to review the program with respect to allocations that it is doing, the intermediate data structures that it is allocating, and remove those allocations. Loop fusion, which Streamly uses, is very good at removing the intermediate data structures in the intermediate in the loops, and reducing big loop iterations is another good idea. The chunked program, what it did was, instead of threading around each path in the entire loop, it was threading around a bunch of paths in the entire loop. So chunking is good at reducing the big loop iterations. So chunking is always good performance-wise. Always review your code from perf perspective, because a lot of times people just write a very naive program and then they expect the performance to be really good, even though they are doing system calls so many times and doing very inefficient things, which you can figure out by doing a very simple code review of the program. Now, modularity always pays, and you can write very modular programs using Haskell, composable programs using the combinators. Modularity lets you focus on the structure of the programs rather than the details. You can have building blocks which are well tested, well benchmarked, and they compose very well. Instead of writing ad hoc monolithic code, we can just compose together very well tested and benchmarked combinators, which will be very reliable, and it will be easy to do. The only thing is that you need a comprehensive set of combinators to compose a wide variety of programs with them. Now, Streamly provides good building blocks, which are modular, composable, concurrent. So you can compose, they are composable, concurrent, yet composable, and they provide high performance. Our focus has always been on high performance. In anything, the performance is the first priority. Now, can we use Haskell for systems programming? The answer is an emphatic yes. We can do as well as any other systems languages. We have seen that Haskell outperformed C and Rust in most of the benchmarks in this particular case study. In some of them, it did not do, C was doing better, but we still have some scope, which if we carefully review and improve the program, I am sure we can do at least as well as C in all cases. We just need to use Haskell correctly and not in a very inefficient and naive manner. Performance usually needs a careful review in Haskell, even though probably in C and Rust, the good performance might be, you might immediately get a reasonable performance. In Haskell, it might not be that great to begin with if you write a very naive program. But if you use very well-tested benchmarked combinators, you'll probably get the right performance in the first go itself. Now, the plus points with Haskell is modularity and refactoring. You can do fearless refactoring with Haskell. And it allows you to write very concise and very high-level code. As we saw, this was the full program that we wrote in a slide. There may be a few more lines there which are available in the GitHub repositories. You can go and check. So this is pretty much the entire program for doing concurrent directory tree traversal, which is recursive. Yeah, that is all. We can take questions now. How much time we have left? I tried to rush through it.
Yeah, we have 10 minutes, Harendra. Okay,
Yeah,
so
sure.
we have one question in the chat section by Julian Shaji. It's, what's the hash curly braces syntax? Is it used to retrieve elements of a record type?
Where was that? Let me go and look at the slide. Hash curly braces dot or
It's just hash. Aditya Kumar has answered her. But again, if you want to check if his answer is correct or not, he has answered. It's used for playing with C directly, peeking C structs, for example. It can be used in HSC files. The HSC2H preprocessor handles the syntax.
Oh, this one. Okay.
I think yes, yeah.
Yeah, so this is HSC. This is to write Haskell and using C data structures in Haskell. So we are basically accessing the dirent member of the structure, the dname member of the dirent structure. So we got the dname here.
Okay.
And the D type here. Yeah. So this is a little, so usually programmers don't need to deal with this. This is the low level code. But if you have to write libraries which are well performing, you need to interface with C, then you may have to deal with HSC. And this is pretty nice, pretty elegant to use.
Thanks, Harendra. Julian, if you have any more questions, you can type in the Q&A section. There's one more question, Harendra, by Jens Peterson. How stable is the Streamly API?
It is very stable. We have a huge amount of testing that goes into it. And earlier, there were some breakages of the internal. Usually, the breakage that happens in the API is of the internal APIs, which are in the internal modules. But now, from this release onwards, we are not even breaking the internal APIs. We are deprecating if we have to change them, even the internal APIs. So you will not see any breakage. There may be very minor breakages here and there in the internal API, but in the exposed APIs, you will not see any breakage.
I think that's all, Harendra. These were the questions. Anybody, if you have any more questions, you can type in the Q&A section. And thanks, Harendra, for joining, for sharing your experience with us today.